So this is my explanation of the optics algorithm. Hopefully this will help me in future to remember it, and it could be something I can use to explain this to other people. I've not seen it described or in quite in this way. I'm hoping I'll start from a very simple version of the algorithm, and then we can add all the other additional stuff as an afterthought, or as a modification to the algorithm. For me, I find it easier to understand this way, and I've not quite seen it explained quite in this way. So the first thing I'm going to do, I want to construct what we call a reachability plot. So the optics algorithm is based around the idea of constructing an ordering of points according to this reachability metric. The reachability metric defines how reachable each point is from the previous point. And in this way, we're essentially going to construct a walk, a directed walk through all of the points, covering all of the points, that defines for each point how reachable it is from the previous point in this ordering. Now, I found at least that without understanding how you achieve this reachability and understanding some more of the mechanics of the algorithm, that concept didn't make too much sense to me. It not enough sense, at least, to work with it in well-informed ways. So the first thing, so I'm going to talk now through how we construct that walk. At each point along the walk, we're going to be walking from one point to the next, and at each point we're going to define the reachability of that point from the previous point. And I'm going to do this in a simplified way that's a little bit simpler than the optics algorithm itself, and then we're going to explain how we enhance that to recover the optics algorithm. So let's say I start from this point here. I'm going to color it in so that we can see what we're talking about. So I'm going to choose a random point to begin with, and I'm going to add it to my list of points that I visited. And for each point of that visited, they'll have a value which we call the reachability. Hopefully all of this will become clear. So I'll choose this point to begin with. Now, that's the first point. That's now the first point in my list. It's chosen at random. It has an infinite reachability because we know nothing, or it could be an undefined reachability, but fundamentally the first point always has an unknown reachability. We don't have any information yet, so we give it an infinite or undefined reachability. So the next thing I'm going to do is look for the next nearest point. Now, the actual optics algorithm is a little bit more complex than this, which we'll come to, but I want to explain it in simple terms. So in this simplified version, we're just looking for the next nearest point. I'm going to imagine that the next nearest point would be this one. So I'm going to pick this point. That's going to become my next point, and I'm going to, for now, call the distance between these two things the reachability of this point from the previous point. Again, little simplification, but hopefully this gets across the core idea. So now we have a list of 2 points. This one has an undefined reachability. This one has a defined reachability. And we'll continue. So now I'm going to, again, I'm going to look for the nearest point. I'm going to look for the nearest point, but this time, rather than the nearest point to this specific point, I'm going to look for the nearest point to all previously visited points. Now, this happens in this example to be the same. So I'm going to step onto this point, which is the nearest to all previously visited points. And let's have a look. So we'll continue doing the same thing. So I'm going to look for the nearest to all of the currently visited points, reaching this point. And let's say that we're going round here. And now maybe the next point, let's let's say it could be this one, or it could be this one. I would say this is a little bit closer, so we'll pick that first. And now maybe we pick this one. So this is where it gets interesting. Now at this point, rather than picking maybe this one that's the nearest, maybe this point here is closer. Now I'm not sure if that's the case in this case, but let's say that it is. So I'm going to jump over here and pick this point. So the interesting thing is that we're walking towards the more dense areas because we're constantly picking the smallest distance that we've seen. So we're constantly walking towards denser areas, but we're not. But by not only considering the last visited point, it gives us a way essentially to go back and backfill. In some sense, if we'd taken a specific route, and we've exhausted the low dense, the near points along that route, we can. It's very easy in this way to go back and revisit to ensure that we cover all of the low, well-connected points. So we'll see. Let's just keep going. We're going along. Let's say like this, and then like this. So this is interesting. Now we've covered the entirety of this cluster, so we can see what happened. We walked into the cluster towards the areas of high density, and then as we exhausted the areas of high density, we walked out to areas of lower density. And now maybe next we might walk, this might be the next one, this one here. Okay, or maybe, well actually I missed this connection here, so maybe we might walk then into a neighboring cluster. And so this might be the largest distance we have, which will then end up doing the same thing here, walking into this cluster in a sense. So we'll do something maybe like this. And as you can see, this is producing some sort of cluster-based ordering, where we find areas of high density, we're walking progressively into those areas of high density because we're in some sense following this density gradient into the center, and then we will see the density gradient in some sense getting, we'll see the area getting less dense as we move to the outer layers of those clusters, and then onto other, let's call them clusters. So this is an interesting way of producing from a multi-dimensional, from some multi-dimensional data, a one-dimensional ordering that in some sense represents how the density of these clusters. We'll see areas that the points that are in the middle of the cluster will be clustered together. The points that are on the periphery will then see the points that are on the periphery of the cluster, and then we'll see points in neighboring clusters. So hopefully that roughly makes some sense for that initial part. Okay, so hopefully now that we've seen how this walk is constructed, we can understand the reachability plot in terms of this walk. So here is an example that I've drawn out by hand of a reachability plot. It's not perfect. But fundamentally, on the x-axis, we have each point ordered according to its order in that walk. And on the y-axis, we have the reachability, so the distance from the current point to the previous point, at least in our simplified view. And you can see here we're walking, we've also coloured the clusters. Now these colours don't correspond to the colours in the previous illustration, but broadly speaking I've coloured the colours according to plots, and you can see how these things end up looking. I'm walking into a cluster, I end up in an area of high density, and then I walk out of the cluster, and then at, let's say in this case, at the peak of minimum density, largest distance, I'll consider this then to be the next cluster that I'm walking into, again walking towards areas of high density. In this case, I've picked the peak, Another approach you could take is you could pick a threshold, so you could draw essentially a horizontal line on this plot, and then you decide that everything above the horizontal line is noise, as these are areas of low density. Everything below the horizontal line is are your clusters. Now, I'm using the word density. That's a little bit incorrect, because as new information appears during my walk, I never update any previous points. So this might not exactly be density, but hopefully it's a metric that represents in some sense how close a point is to previous points, and therefore we expect the points where this value is low to be areas of high density, and where it's high we expect it to be an area of low density. So if I picked a horizontal cut of this, that would correspond, at least in my understanding, would correspond to a particular run of the dbScan algorithm, which has this density as an input, has this distance as an input, or let's call it distance. So the interesting thing here is that we've been able to run many iterations of the dbScan algorithm with a minimal additional cost. Another approach that you might take to doing this clustering is that you might look at this gradient here as we're coming out of the cluster to determine that the cluster is in some sense finished. So you might look at these gradients and decide, well, things are thinning out pretty quickly right now, so we'll call that cluster done. And that's an interesting approach because it allows us to account for different clusters of different densities. One more thing to note as an aside, since the reachability in this case is defined in terms of the previous point, or the distance from the previous point, if we had a threshold, we typically would also maybe take the point to the left of the threshold as well, so that because it's defined backwards, because the distance is defined backwards, it's defined to the point that's furthest away from the center of the cluster, let's say. So that it makes sense to also include that point, as it's probably in a denser region. I'm not sure if that explanation makes sense, but hopefully if you think about it for a little bit, you'll realize that as we approach the areas of density, given that that I only have information from the past, not from the, in some sense, present, I don't have information from the current point, then you'd want to backtrack by 1 point. So that's broadly speaking the reachability plot. That's broadly speaking the reachability plot. Let's go back now and look at the ways in which we simplified. So I've been describing this as reachability, but this isn't reachability in the sense that it was defined in the optics. This is just distance. Reachability is a little bit more of a sophisticated concept, but only for, as I understand it, 2 reasons. One of them is performance. We want something that runs faster. And the other is smoothing, that we want the reachability plots to be a bit smoother than a pure distance metric would give us. Okay, so hopefully we can look at how these two additions can be made. The first one is very easy to understand. For any given point, I want to consider. It's very performance intensive to consider all of the other points in the space, so I only look at points within a specific radius, so a specific user-defined radius. And so let's say when I'm considering this point, maybe I'll consider only these points within the radius here, and then when I add this point, I'm only adding these points within the radius of that point to the points that are being considered. So at every step I consider all points within a user-defined radius of all previous points, and I take the minimum distance of all of those points. And hopefully that makes sense. The other enhancement, as I understand it, is to smooth the reachability plot. The core idea is that we don't, if we have areas of, I don't want to consider distances of points that are very dense together. I suppose that's one way of saying it. Or if the points are within what we call the core distance, then I want to treat them all equally. And we define the core distance as the distance in which there are at least n different at least n points. So let's say I'm looking at this point, and I might, if n equals 3, and n would be a user set thing, then I've got maybe 1, 2, 3. Maybe these three are the closest, and therefore I'll define my distance here. Now the distance definition is a bit more complex because points can be at the same distance, but fundamentally it's the distance in which I have I find those 3 points and any other points that might be at the same distance as those. So for example, if I pick this one, I might end up with 4 or 5 points if they're all at the same distance. And then we say that is the minimum distance the minimum distance resolution that we want to see, and that is obviously going to be dependent on the density. So in areas of high density, that's going to be a small value. In areas of low density, that's going to be a big value. And this will have the effect of smoothing out that curve so that we don't see big jumps. We don't see artifacts of the both ordering and the let's say fine structure of these clusters. And that's it. So with those 2 additions, now one thing to note is that, and I think this is why one of the reasons why it's maybe called reachability rather than distance, is that now in this new formulation of quote-unquote distance, this is an asymmetric metric, so the distance from this point to this point is not the same, may not be the same as the distance the other way around, because we're considering the density, the other points in the neighbourhood as well. However, so this is what now gives us our new reachability, but I think it's fair to say that broadly the core idea is still the same. We're still walking in the direction of density, or towards high density areas, or hopefully towards high density areas based on the reachability information that we already have. And then we're constructing these reachability plots and using those reachability plots then to extract clusters. I hope that helps. That's my understanding of the optics algorithm.